All right, guys, in our last video, we talked a little bit about the quadratic formula and how the quadratic formula can be used to find the x-intercepts of a quadratic function when those x-intercepts aren't, nice whole numbers. And I mean, I guess I should say this too. You could use that to find the x-intercepts regardless. It could be something that's factorable, and maybe you're not comfortable with factoring. You'd rather put it into quadratic formula. That's fine. You can do that with the quadratic formula. But it was initially designed to get those numbers that are not as easy to factor and understand on their own, right? And after that formula was kind of rediscovered by the Western world during the Renaissance, people continued to work on it, and the question came: what happens when you take a quadratic function, like the one we see here in this image? Take a quadratic function that doesn't have any x-intercepts, or we can see here it doesn't cross the x-axis, so it has no x-intercepts. And what happens when we put that function into the quadratic formula? Okay, so let's actually take a look at that and let's see what happens here. Remember that your quadratic formula, guys, is going to be negative b plus or minus the square root of b squared minus 4 minus 4ac, all divided by 2a. So we can just plug these values in from this function into this equation, just see what happens. Let's first identify what our different parts are going to be. My a value for this would be, over here I have x squared. I only have one x squared, right? There's nothing else there, so I know my a value is going to be 1. And then my b value is this middle one right here. It's minus 6x, which means that this has to be a negative 6. We're only taking those coefficients, right, guys? Nothing else. And then my c value is going to be this last piece right here, which is a plus 11 or a positive 11. We can just write that as 11, right? Okay, so those are going to be my values for the quadratic formula, or that I'm going to put into the quadratic formula. And we can just go ahead and start doing that and simplify and see what we get. Okay, so my negative b is going to be negative 6, and a negative number is a positive number, right? So we can just write that as 6 plus or minus the square root. I'm going to have my 6 squared here, or b squared, which was 6, minus 4 times my a value, which is 1, times my c value, which was 11. And that whole thing is going to be divided by 2a. And my a value again was 1. Okay, and we can start simplifying this, right? We can start simplifying this and come up and figure out my solutions, or our solutions, pretty easily. Negative 4 times 1 is negative 4. Negative 4 times 11 is going to be negative. Let's switch colors here, actually. Negative 11, negative 44. So this piece right here I can rewrite as a negative 44, and then 6 squared is going to be 36, right? And 2 times 1, well, that's easy, right? That's just going to be 2. And so now I can simplify this. On the inside of my radical here, I've got 36 minus 44. 36 minus 44, hopefully you guys are getting there and figuring that one out, is going to be negative 8. Right, so let's rewrite this equation. This is going to be equal to 6 plus or minus the square root of negative 8, right? 36 minus 44. Did I say 8 before? It's negative 8, excuse me. All divided by 2 on the bottom, okay? And I mean, this is drastically simplified from what we just barely saw, right? But I think we can go one step further. Let's take a look at this radical. And if you remember back from our video on radicals, on simplifying those radicals, this hopefully is becoming an easy process. And some of you might even already be able to see, oh, square root of 8. Well, technically this is negative 8. We'll get to that here in just a second. The square root of negative 8. And you already know what that's going to be. But let's do our factor tree and come up with our factors of negative 8. And remember again that this is a negative 8. So let's just keep going through here. So I'm going to have to start. To get a negative number, I have to have one positive and one negative, right? So we could say negative 2 and positive 4. And then factors of 4 are going to be 2 and 2. How about this -1 or -2 right here? Realistically, guys, this actually can simplify as well, and this is what a lot of these mathematicians realize early on, but this can simplify to -1 and +2. Not that that's going to make a huge difference here, but I want us to identify that our -2 factor can simplify to -1 and +2. That's going to make this process a little bit easier. So since it's a square root, we're looking for sets of two numbers, and we've got one set of two numbers right there, but then nothing else, right? So we're going to leave that -1 and that -2 in there, and we're going to write those separately for a very specific purpose here, which hopefully will be evident in a second. So let's rewrite this now. So I got 6 plus or minus, I'm going to put my 2 on the outside, right? And then on the inside, I'm going to have 2 times a -1. Hopefully you can tell if that's a 2. It looks a little bit like a Z. It's hard to write them on the sketch pad here. So 2 times -1, all divided by 2. Okay, and we can simplify this, right? I got these two factors up on top. I got my 6, and I got my 2 square root of 2 times -1. But we can factor this because I can pull a 2 out of both of these, right? The 2 and the 2 can cancel out here, and then the 2 and the 3 will go into 6, so those can cancel out. So let's rewrite this statement again and factor out that 2 out of this whole thing. So instead of 6, I got 6 divided by 2 again, which is 3, and then 2 divided by 2, which is just going to be 1, which is going to leave me with my radical here, which is the square root of 2 times -1. Okay? And we can take this one step further. If you guys remember from our discussion on exponents and what we can do with exponents, realistically what we have here is we've got an exponent on the outside here with two numbers being multiplied on the inside. If you remember, I think it was rule number what was it, 5 or something like that, just the distributive property of exponents. I can just distribute this square root sign through to both of these pieces. So we can rewrite this now as 3 plus or minus the square root of 2 times the square root of a -1. And what these early mathematicians realized was, I shouldn't say early, Renaissance mathematicians, some of these or these Renaissance mathematicians realized is that this was as simplified as this was going to get, and that they couldn't do anything with this square root of a -1. They didn't know how to express that. I mean, we could if we were looking at the square root of this 2 here, we can figure that out, and that's something that they could calculate. I mean, they may not want to, but they could calculate that, and you get like 1.4 something or other, right? But the square root of a -1, there's really no way to express this except for leaving it exactly like that, because I can't take two numbers and multiply them and get a negative number out of it, right? One would have to be positive, just like we saw when we were factoring this. One has to be positive. I had to have a -2 and a +4, or a -4 and a +2. No other combination would have given me -8, right? And so they realized that, and for the ease of writing this and simplifying this, and partially I think also because they didn't fully understand what they had discovered here, is they decided to call this square root of a -1, square root of a -1, an imaginary number, which is an awful name, and you've heard me complain about that before, which they would express with this little cursive I like that. The interesting thing is that even though they called it imaginary, they didn't understand all of the implications and all the places where it was relevant. The interesting thing about that is that it actually exists all over the place. And in fact, as we started to understand more mathematics of the world, or of the universe, we started to realize how important this concept was. A couple of examples, you've probably heard me say this before, but if you're dealing with any sort of mathematics dealing with the subatomic world, this is a huge concept, and it must exist, or else we can't explain what's happening on a subatomic level, right? airlines. If you've ever gotten on a plane, I guarantee you that pilot and the guys in the tower, all of them are doing this, right? They're all using this concept. It's really useful when we talk about mapping and expressing coordinates. And then computer software, right? It is another place where this is an important an idea, and is the only way that we can make certain concepts work within computer software. Anyways, so they express this as an I, and so we could just go one step further here, inserting this I now into our equation, and we would finally get, and I think that hopefully you guys have followed this and understand this, we would get our final solution, which would be 3 plus or minus the square root of 2I. And this number right here, by the way, guys, this imaginary number, you've probably heard this term before, imaginary numbers. It's one of the few, or another type of number, like we've got rational numbers, irrational numbers, whole numbers, natural numbers, right? And maybe we should spend some time here in the future and talk about those distinctions. But this number right here, where we've got not only imaginary numbers, right? We've got this imaginary piece right here. We also have this 3, which is a very real number, right? And so we call this complex numbers. When we have a mix of real numbers and what are called imaginary numbers, even though, as I already mentioned, they're not imaginary, they do exist all over the place and are incredibly useful in a lot of mathematical concepts. These imaginary numbers, when combined with real numbers, are called complex numbers, right? Complex numbers. Okay, hopefully that makes sense for you guys. And always, if you guys have questions, shoot me a message, come in and chat with me. We can go over this. You'll see examples like this also in your assignment. Okay, thanks, guys.